Hello, my name is Josiah, and here I will be presenting the work ALGES, Active Learning with Gradient Embeddings for Semantic Segmentation of Laparoscopic Surgical Images. First, we give a brief overview of active learning, which is a learning paradigm that mitigates the problem of having limited labeled data for training machine learning models. Typically, in the supervised setting, there exists some quantity of curated labeled data that is used to train some kind of model that can make predictions given unseen data. However, performance of the model on the given task is highly dependent on the amount of quality data available. But what if we have access to a large amount of unlabeled in the wild data, as is characteristic of real-world scenarios? This is where we can introduce an external oracle, or a human in the loop, such as a clinical practitioner. We can smartly select some of the unlabeled data we have access to via some criterion, and this data can be rigorously labeled by the oracle and introduced into our existing labeled dataset. This will result in improved model performance, and the newly trained model can even inform the criterion we use to select more data for the oracle to annotate. This is the active learning loop. We want to achieve the best performance possible given some restrictions on how much data we can label, and to ensure efficiency, we need to choose a good criterion that will avoid acquiring a dataset with redundant or nearly similar data samples so that the model can learn obscure or out of distribution data points. In this work, we ask, can we use information intrinsic to the model training process to design a good criterion for selection? Thus, we present ALGES, a new active learning framework designed for segmentation, which is delineating regions of an image into different classes, such as anatomy or instruments. A key insight of our work is that fundamentally, gradients induced in a model that are used to train a network intrinsically encode information of how unsure a model is about a particular data point. In other words, data that induces large gradient updates to the model are data that need to be learned by the model to improve its performance. Our method works by taking unlabeled data, in our case frames from surgical video, and passing this data through a model that has been previously trained on some limited data pool. As is customary, we derive some loss, with which we can take gradients with respect to the weights of our network to update the model. We consider gradients from the last layer of the network and observe that each pixel of a given n by m image contributes some amount to the gradient updates of the weights of the network. If we look at a single pixel's contribution, we can take the Euclidean norm of the gradients for that pixel and derive a quantity analogous to model uncertainty for that pixel, and in turn, imagine a heat map of uncertainty for that image. From a different angle, we can consider the gradients for a particular output class and aggregate gradients as a vector summarizing model uncertainty for a given output class, for example, regions of the abdominal wall. As a testbed for our method, we use CollectSeg 8K, the largest public dataset of surgical video frames with dense semantic segmentation labels. This dataset consists of 80,080 frames extracted from 17 videos of laparoscopic cholecystectomies, which is a common surgical procedure involving the removal of the gallbladder. We show our method performance in contrast with several other active learning algorithms in the literature. Our method performs well in low data settings, making it suitable for settings where annotation cost is high, as is the case in many biomedical applications. Thank you for listening, and please visit our poster for more details.